In this video, we're going to learn about directing groups. So directing groups are substituents that already exist on a benzene ring, and when you go to do a subsequent electrophilic aromatic substitution reaction, they dictate where that reaction will occur on the benzene ring with reference to the existing substitution. So directing groups are kind of like a traffic cop. They are standing in the intersection and they tell you, okay, you can drive forward, you go to the right, you stop. Directing groups tell you where the next reaction will occur. So there are two types of directing groups. Our first type is the ortho-para directing groups. So in this example, the group indicated by the letter G is an ortho-para director. So when an electrophile is introduced and the EAS reaction occurs, the products that you're going to get are going to be majority ortho and para, and you're not going to see any of the meta product. In this next example, I've used the letter M to dictate a meta director. So if this type of group exists on the benzene ring and that benzene ring is exposed to an electrophile in the right conditions, you're going to end up with a meta substituted product, and you'll see no ortho-para products or very little of the ortho-para products. So let's talk about ortho-para directors. Ortho-para directors are pretty easy to spot. They have a lone pair on the atom directly attached to benzene, or they are alkyl or aryl. Another thing about ortho-para directors is that their presence tends to make the benzene ring more reactive, so we call them activating. So that means that if they are on the benzene ring, any subsequent reactions are going to happen very readily and very quickly, and possibly in very light conditions, maybe without a catalyst or maybe without heat. The exception here would be halogens. So notice that a halogen on a benzene ring would actually have lone pairs on the atom that's directly attached to the benzene. So a halogen is an ortho-para director. Any reaction that will occur is going to happen in only the ortho or para position. However, halogens are deactivating. Their presence on a benzene ring actually decreases the reactivity of the benzene, and that's because they are electron withdrawing and they do not have resonance with the ring. So we'll talk about that in more detail in later parts of this chapter. So let's talk about why. Now, the reason why really comes down to a couple things, and one of the big ones is the resonance forms of the ortho-para directors. So if you have an ortho-para director such as aniline, notice there is a lone pair on the nitrogen atom, and the nitrogen atom is directly attached to benzene. That's going to make this an ortho-para director. So we have an attack of the pi electrons on the electrophile. And you add the electrophile in the ortho position. That gives you a carbocation in the meta position. Now, if we take these electrons and move them over, we get a new resonance form where the carbocation is still meta to the aniline, but now it's across the ring, it's para to the electrophile. We can move the electrons again to create a new pi bond. And now we've put the carbocation directly under the aniline. Now, this is actually a really good thing because what this shows us is that there is a resonance form here with the nitrogen and the carbon below it, where we can actually delocalize the positive charge onto the nitrogen atom. So since the amine lone pair is able to contribute to the resonance forms, that's going to be more stabilizing. And you can actually see very similar resonance forms for the para attack, which would be a really good practice problem for you to do yourself. Now, if you were to do a meta attack with an ortho-para director, we're going to take the exact same starting material, add an electrophile, and notice that I've put the electrophile in the meta position. This puts the carbocation ortho to the aniline, And we can move the electrons around the ring the same way that we did previously. Until the carbocation is para to the aniline. Notice what we never are able to do with this structure is have the lone pairs on the nitrogen contribute to the resonance. If we did that, we could push the electrons over here, but that's not going to do anything to satisfy this positive charge. What we would end up doing is just creating a separation of charge, which is never going to be a good idea. So there's actually one less resonance form here than there is for the ortho or para attack. So while we're still thinking about ortho-para directors, let's also discuss the concept of an activated benzene ring. To do this, we're going to compare two molecules. We're going to look at aniline and an amide made from aniline. So both of these are ortho-para directors because the lone pair on the nitrogen is on the atom that's directly attached to benzene. It's not removed by another carbon or anything like that. So these are both ortho-para directors. But notice that with the aniline, all of the resonance forms push into the benzene ring. So we can show that through resonance that the aniline actually pushes electron density into the ring. And we know that the first step in an electrophilic aromatic substitution after the formation of the electrophile is for the pi electrons to attack the electrophile. So in order for a benzene to be more activated, we want it to be electron rich. So anything that you can put on the group that is going to be electron donating instead of withdrawing is going to be a good activator. Now our amide also has resonance into the benzene ring. We could move the electrons around the benzene ring in the same way. But the additional thing that this structure has is resonance in the other direction. So because of the presence of this carbonyl, we actually have an electron withdrawing effect as well as a slight electron donating effect. So while this ring would be more activated than a ring that has a meta director on it, which we'll talk about in a second, but it's going to be less activated than the aniline. So aniline is actually a very highly activated benzene ring. You can get almost any reaction to occur very readily with aniline. But with our amide here, it's going to be a little less effective. So what does this mean for reactions of benzene derivatives? Another type of ortho-para director is an alkyl or aryl group. So remember, aryl means a benzene ring, something aromatic, and alkyl just means an alkane. So in this example, we have toluene, which has a CH3 group. This is an alkyl substitution. This is an ortho-para director and also an activator. So that means that when we go to do the reaction with nitric acid and sulfuric acid, which is a nitration, we are going to get the ortho product, we're going to get the para product, we're not going to see very much of the meta, and this reaction is going to occur very readily. We're probably not going to have to heat up the reaction or add in any additional catalysts. And our product breakdown is actually 59% of the ortho product, 37% of the para product, and 4% of the meta product. Now I want to look at something real fast. It's a pretty easy hypothesis to come by that the para product should actually be the major product in any reaction, because when you think about it, the further apart these two groups are, the less sterically hindered they are. But what you'll actually come to find is that unless the existing substituent is massive, like think cyclohexane or a T-butyl group, the steric effects are actually very little. And since this group is electron donating, what we'll actually find is that the ring is going to be a little more electron rich in the ortho position. And so the ortho position is actually going to be the stronger nucleophile here. So you're often going to see a lot more of the ortho product unless it's very sterically hindered. Our next topic is meta-directors. Meta-directors have a positive or partial positive charge on the atom that is directly attached to benzene. These groups are going to be electron withdrawing, and they are also going to be deactivating. So a really good example of a meta-director is the nitro group. It's really easy to forget about the nitro group because you think nitrogen, you think lone pairs, and you think ortho-para. But you have to remember that the structure of the nitro group is actually that it has a positive charge on the nitrogen and a negative charge on the oxygen, and that's what keeps it as a neutral group. But this positive charge on the nitrogen actually makes this group electron withdrawing. So electron density is being pulled from the ring and into the nitro group. The other interesting thing about meta-directors is that depending on how a functional group is attached to the ring, they can be either meta-directors or ortho-para directors. For example, depending on how an ester is attached to a benzene ring, it can be either a meta-director or an ortho-para director. So take a look at the examples that I drew in the top right corner and decide which one is an ortho-para director and which one is a meta-director. Hopefully what you noticed is that the carbonyl being directly attached to the benzene ring is going to have a partial positive charge. And so the first structure I drew is actually a meta-director. But the second structure has lone pairs on this oxygen, and the partial positive is all the way over here. So since this oxygen has lone pairs and is directly attached to the benzene ring, this ester, even though it has the same number of carbons and is very, very similar, is actually an ortho-para director. So let's look at our example down below of the nitrobenzene. So when nitrobenzene is reacted with nitric acid and sulfuric acid, nitrobenzene is a deactivated structure. It's probably going to actually take heat in order to get this reaction to occur. I've drawn the three possible products here, but what you're going to see as your product breakdown is 6% of the ortho product, only 1% of the para product, and 93% of the meta product. So not only is the meta product major, but it's really the only product that counts here. We don't have to think about the ortho or para products at all. Usually when you're doing a reaction with an ortho-para director, you're going to end up drawing out the ortho and the para products. Usually determining which one is major is pretty tricky, so I tend to not ask that. But with a meta director, the meta product is the only one that you need to draw. So why does this happen? We're going to compare resonance structures again. So let's take a look at the meta attack. So if these electrons attack the electrophile, we can draw this first structure of the resonance forms here. Notice that the carbocation is ortho to the nitro group, and we have the electrophile in the meta position. We can move the electrons around the benzene ring the same way that we have with all the other resonance forms. But what you'll never see is the carbocation directly attached to the nitro group, and that's a really, really good thing. We'll see why in this next example. So when you do an ortho attack with a meta director, you end up with a problem. So we have our initial attack, we put the electrophile in the ortho position, the carbocation goes into the meta position, we can bounce it around the ring, the same way that we did with everything else, and then we end up with this disaster right here. Two positive charges directly next to each other. That just doesn't happen in chemistry. That is wildly unstable. Why would there be an attraction of any sort between a positively charged carbon and a positively charged nitrogen? Not only would that not form, but if it did, it would probably just fall apart. I don't see how that would work. So this is why we're going to get the meta product, or we're not going to see any really of the ortho or para, is because there is a resonance form that is a true disaster. So on this last slide, I have some practice problems. I want you to take a second and work on these on your own. So go ahead and pause the video. Okay, so assuming that you paused the video, we're not going to draw out any intermediates or anything like that. We're just going to look at the products. So in this first structure, we have toluene, we have a methyl group. The first thing that you want to ask yourself is, what type of director is this? Is this ortho-para or is it a meta-director? And this is an ortho-para director. So we take our ortho-para director, it is activated, we're going to react it with nitric acid and sulfuric acid. That is a nitration reaction. So what we're going to end up with is the ortho product and the para product. Now looking at the next reaction, we have acetophenone. Is this an ortho-para director or a meta-director? Hopefully you recognized that this carbonyl being attached to the benzene ring makes it a meta-director. Remember, that's because there is a partial positive on this carbon. That's one of the first things that we learned about carbonyls, is that there's a partial positive on carbon and a partial negative on oxygen. So that makes it a meta-director. And then we are doing a bromination. So this ring is deactivated, but bromination occurs fairly readily on a benzene ring, especially because of this catalyst. So we don't really have to worry about whether or not this reaction is going to occur. And the only product I want to see from you is the meta product. Now, in our last reaction, we have a nitro group and we have a nitration occurring. So this is a fairly deactivated ring. Let's go ahead and assume that I put heat here. Typically, I try to give you a really solid hint that a reaction is going to occur even on a deactivated ring. The nitro group is meta-directing, so we want to put our next nitro group in the meta position. Now, this is our product after step 1. Step 2 is asking us to do a Friedel-Crafts reaction. So I want you to think back to when you learned about Friedel-Crafts and then you learned about the limitations of Friedel-Crafts reactions. One of the limitations was that on a deactivated ring, Friedel-Crafts just will not occur. And if you look at the product we just drew, we have 2 nitro groups on here. Not only are these groups deactivating, but there are 2 of them. So this is just not going to happen. Our final product will be our product after step 1. And in fact, it actually would not even occur even if we hadn't done the first nitration. If there were only 1 nitro group on this benzene ring, the Friedel-Crafts reaction still would be unlikely to occur.